Okay, good morning, everyone. Today we have Dakshita Khurana, who will tell us about the emerging field of quantum crypto and connections to complexity. And she'll be here today and tomorrow if you want to chat. And I also want to mention that today in the members seminar, there is a discussion about Alpha Evolve and various ways AI is useful for mathematics, might be of interest. Okay.
So thank you, Edith, for inviting me. As Edith said, I'm around today and tomorrow and happy to chat after. Okay, so I'm going to talk about quantum cryptography, and the subtitle is Why Quantum Cryptographers May Sleep Better Than Classical Cryptographers. And the small story here is that as a classical cryptographer up until 4 years ago, I used to worry a lot about whether classical cryptography can exist and what complexity do complexity theorists need to prove in order for classical cryptography to exist. And I started doing quantum cryptography over these last few years, and I can sleep better now because it turns out we need less from the complexity theorists in order to do quantum cryptography. And so let me hear more about that as the talk proceeds. I want to start out by saying that this is based on joint work with my amazing student, Kabir Tomer, at UIUC. Okay, so as I was saying, cryptographers really want to build cryptography without having to make any unproven assumptions. This is the holy grail. Secure classical cryptography can exist only if P and NP are different. And actually, you don't just need P not equal to NP, you also need this stronger assumption, which is that one-way functions, which is a really basic crypto primitive, you need them to exist. Now, what is a one-way function? This is a basic assumption necessary for all of classical cryptography. It's just a function that is easy to compute, but hard to invert. And when I say hard to invert, what I mean is that if I sample a random x in the domain of the one-way function and give you the output of the function computed on this input, then it is hard to reverse sample this input or in general any input that matches the same image. This is a simple definition. And just going back, we need this one-way function primitive to exist in order for any interesting or nearly almost all interesting classical cryptography to exist. Now, on the other hand, in quantum land, there was this major achievement that was already unlocked back in 1984, which is Bennett and Brassard showed that you could build quantum key distribution without making any unproven computational assumptions. And so while this is really interesting, here's a very natural follow-up question. Can we quantumly realize other cryptographic primitives? For example, zero knowledge, secure computation, signatures, encryption, commitments, and so on, without making any unproven assumptions, while obviously using quantum resources, because we know we cannot do this classically.
Key distribution give you some of them.
Sorry?
Key exchange.
No,
Key exchange.
none of these.
Yeah.
Key exchange, quantum key distribution, no, it doesn't. We could talk about some notions of public key encryption, but like in interesting notions, you want a usable public key that can be copied many times and so on. Key distribution doesn't seem to. So can you realize these really useful, interesting cryptographic primitives without making any unproven assumptions? And don't worry if you haven't heard of these before or if you don't know what these are. Anything that's relevant to this talk, I will explain. And if it still doesn't make sense, please just interrupt and ask. Okay.
Following up on Avi's question, is the problem that like somehow what you get out of key distribution requires interaction to do these things, or you can't even do these things with interaction?
No, it requires interaction, and it has public keys that cannot be copied many times, which obviously for a public key, you need it to be some type of state that can be copied and distributed many times. On the other hand, if the adversary, like if you were to naively use quantum key distribution to build a public key encryption, then the key that you would end up with would be a quantum state. And if the adversary happens to have copies of the state, then your system is broken. So turns out that you need, or you seem to need, some type of mathematical hardness to do better than that. All right, so here's the roadmap for the rest of this talk. I'll first talk about lower bounds. So, this question of classical cryptography cannot exist if P equals NP. What type of complexity lower bounds do we need for quantum cryptography to exist beyond QKD? And then in the second part of the talk, I will say a little bit about how to build quantum cryptography from better, in some sense. They're really going to be incomparable, unfortunately, but at least new ways to build quantum cryptography from assumptions that are very different from the ones that we use to do classical cryptography. For example, if you've heard of RSA, they give you certain types of classical crypto systems, and we'll see some quantum analogs of some of these, well, not really analogs of these assumptions, but different quantum assumptions and how to build crypto. As I said, feel free to interrupt me anytime. Okay, so let's start out with some small, a little bit of crypto background. Public key encryption is this really fundamental cryptographic primitive that allows a user to post a public key while keeping a secret key hidden with them, such that anyone can generate an encryption with respect to their public key of any secret message in such a way that the original, the party that generated the public secret key pair can decrypt using their secret key, whereas no eavesdropper that's eavesdropping on this network and knows the public key and arbitrary ciphertext learns anything about what message was being encrypted.
So for this definition, the public key is classical.
Correct. Yes. So that was the thing I was going to say next. Everything here looks classical except the secret key, which has a ket notation around it. And again, I'm not assuming any quantum background, but whenever this ket appears, this is a quantum state, not a classical string. And a quantum state is different in that, well, we'll talk about properties as and when we need them. I don't
So sigma is also classical?
Sigma is also classical. Here, it could be quantum in general. In this example, it's classical. It doesn't really matter. Okay. Another option, and going back to Avi's question, is you could think of the public key being quantum and the secret key being classical. And that's another valid way to define public key encryption in a quantum setting.
But
yes.
if the public key cannot be cloned, then why?
Good. Because you could have a clonable state be your public key, such that you can clone the state many times and distribute it. And yeah, and that would be a good definition also.
What's a clonable state?
What is a clonable state? Good. So a clonable state is a state for which there is an efficient quantum circuit that takes one copy of the state and outputs two copies. Now you can keep applying the circuit to generate as many copies of the state as you want. And this is what I mean by a clonable state. Hopefully this is what we find. Okay.
And it doesn't make sense to have both of them be quantum?
Great question. It does. We don't really know anything interesting I don't know anything interesting that I can say about that scenario, so I'm not going to include it here. And so open question, when you have public key and secret key both be quantum, what lower bounds can you derive? I do not know. It's very tricky to get a handle on things then. All right. I'm just going to very briefly also talk about signature schemes. The reason is here also you have a public key, which is now called a verification key, and a secret key, which is sometimes called a signing key. So you again have a public secret situation here, and where you want that there is this ability to sign messages given the signing key, such that no forger is able to sign messages unless it also has the signing key with it. The main reason I'm showing you these examples of encryption and signatures with like quantum secret keys here or potentially quantum public keys and classical secret keys is to talk about the nature of hardness in these settings. So in all of the settings that I showed you, at the very least, we wanted some efficiently sampleable public and secret key pairs such that given many copies of the public key, or you make it clonable, or you at least allow the adversary to get many copies of the public part, it should be hard to output to find the secret key. This is the minimum you need for any public key encryption or signature or so on to exist. Or in the case where the secret key is quantum and the public key is classical, you just say, I give you the classical public key. It should be computationally hard to generate the secret key state given the public. So this is, obviously, we at least need this. Often we need a lot more. So let's break it down even further because we're looking for lower bounds. Trying to say, what is the least we need here? And Morima and Yamakawa asked this question back in 2022, and they defined this primitive called a one-way state generator. This primitive intuitively captures the hardness of guessing a classical secret key corresponding to some public quantum state. So in other words, there is this efficient state generation process that takes a uniform key as input and outputs a quantum state. And the hardness here is that the hardness requirement is that no polynomial time quantum circuit that is given many copies of the output state cycle should be able to find any key whose state output by generation procedure overlaps with the target state cycle. So this is just like the one-way function guarantee, except the function output is now being replaced by a state.
Style K prime is the prime.
Sorry, say that again.
The style K prime is the prime.
Oh, right. The prime should be on the K. Yes, thank you. Thank you.
These are states on any quantum bit. The states have n quantum bit.
Correct. Yes, these are efficient. These are generated by an efficient state generation process, and so they are on polynomially in n quantum.
So can you remind the notation in the last line?
Yes. So the clarification was that the prime should be on the.
No, but what does it mean?
Oh, what does this mean? Good. So when you have two quantum states, you can compute the overlap between them. So this is the inner product between the two states, which is basic. Sorry.
Correlation.
Yes, how close the states are. You can think of it as, you can also define this in terms of a quantity called trace distance or fidelity. These are just, different measures of computing how close two states are. So all this is saying is that if I were to try to compute how close these states are, they should be really far from each other. And by really far, I mean, their overlap should be zero. And overlaps can be computed on a Hilbert space, but I don't want to go into all of that. So you should just think of this as this state, if you were to measure it, if you were to take this state and apply a measurement and observe what it gave you, that outcome should be different from what the other state gives. And this should happen no matter what you do to the state before measuring.
But the state is a vector in a Hilbert space, so it goes to dimension 2 to the end.
Yeah.
And this notation is not standard for us. It's just notation.
It's not
your product.
Yeah,
It's standard in quantum computing. I'm just saying.
But
It's just the inner product of two vectors.
this is just the inner product of two vectors. You represent these two states as vectors and you take their inner product. This literally is what you're doing. Yes. Okay. Good. So, right. So we were talking about what a one-way state generator is, what a one-way state is. And the reason this came up, you have a question?
Continue, maybe you'll answer the question.
Okay, the reason this came up is we were trying to distill down this minimum type of hardness that we need in order for public key encryption and signatures and so on to exist. Can we simplify this even further so that there's no quantum states involved? Like I am a classical cryptographer by training. The less the quantum involved, the nicer I find it. So perhaps we could find an even simpler primitive. And so in this work with Kabir, we defined one-way puzzles, which is an efficiently quantumly samplable hard-on-average problem. So what do I mean? There's an efficient quantum sampler that outputs pairs of string X and Y. Well, that you can say satisfies some relation. You can always define a relation. and you want the sampler to always satisfy this relation, such that given y, it is hard for a polynomial time quantum machine to find an x that satisfies the same relation.
So X and Y are classical.
X and Y are classical. These are strings. There's no ket around them. These are all strings. All that is quantum here is the sampler, and you can just black box it as some machine, and it's outputting this distribution over X and Y. And all you need is, given Y, it should be hard to find an X that satisfies the relation. Now, importantly, this relation is not necessarily efficiently computable. Given X and Y, it's not necessarily efficient to check whether R X Y equals 1. And moreover, if the sampler was classical, then you can define this in a way that R is always efficiently computable. I won't get into the details of all of this, but I just want to emphasize that this relation is not necessarily efficient. This is going to be useful for us later on.
So we should think a sampler or a puzzle is a pair of the relation and the sampler, the quantum algorithm that samples it?
Correct, yes, yes. Although I'm going to give you a simpler definition soon, where you won't even have to think about the relation anymore, but this is how it is first defined. Okay, sorry. So what we want to do in order to get a one-way puzzle, in order to build a one-way puzzle, is to somehow capture this hardness of, let me go back, of inverting quantum states to find their input classical strings, and instead define this problem where I have a classical output string, and the hardness should be in finding a classical X corresponding to the Y. So I somehow want to I want to show that the existence of one-way states implies the existence of one-way puzzles, which means I will have to convert these quantum states that the one-way state is outputting into classical strings, and say even these classical strings are hard to invert and recover the input X. Okay, so just to be clear, like this is what is going on in a one-way state. You have an output quantum state. The hardness is in finding K. From this state, I want to generate some classical piece of information Y, such that given Y, it is still hard to find K. So this is what the goal is. Okay, so if that makes sense, I'm going to introduce now one quantum tool. We will just use this as a black box tool. This is called efficient shadow tomography. What this does is it takes sufficiently many copies of a quantum state and captures the information inside the state into what are called shadows. Shadows are nothing but random measurements of the state, this particular case. So you basically take the state and you apply random unitaries to it. Don't worry about how to apply them and so on. Just believe me, this is efficient. Like you don't actually compute truly random unitaries and apply them. You do something that is efficient and that has a similar effect as applying random unitaries and measuring the state. And at the end of this process, you collect a bunch of classical measurement outcomes that are called shadows. And the amazing property that Huang, and Priscilla showed that these shadows have is that given the shadows and any key K, there is an inefficient estimator that will estimate the overlap between phi K and the state psi, where phi K, maybe this should have been psi K, sorry, but this was the state corresponding to this was the output of the state generator corresponding to key K, that was the state, and your input state psi, of which you took the shadows.
So this is an information theoretic result.
This is an information theoretic result, yes. Yeah. So what this is saying is you can take a state, and by computing these shadows, you can approximately learn a set of many overlaps of the existing state with a bunch of different phi Ks. Okay, yes?
So is this for like a specific state?
Good, I'm coming to that.
Or is this like general for any, like?
Yeah, this is true for any psi. You can compute the shadows. And now for every K, your estimator will give you the overlap. Now, what guarantees does this estimated overlap satisfy? Again, when I say overlap, it's just the inner product. What guarantees does this satisfy? This is the formal guarantee. let me just complete this. And with high probability over the randomness of computing the shadows, for every key, this expectation is close to the right value. So that means you can compute a set of exponentially many overlaps, and they're all going to be nearly correct. Yes.
Is the number of copies linear in N?
Yes.
And is it important for
It can
you?
be linear. No, what is important is for it to be any polynomial, but in their case, they can have it. Yes.
So the shadow is obviously it's a quantum algorithm. The
Yes.
estimator is a fully classical algorithm. Or
It's it's not efficient.
it's not efficient.
Yeah, it's fully classical, but it doesn't matter. You give it a classical string, it gives you a classical string output. So think of it as like a black box that given was.
What's the role of K here? So because
Yeah, good. The role of K is, so my goal is to take this out, recall what the goal was. Just let me go back here. The goal was to convert psi K into some piece of classical information such that there is hardness in going from this classical information back to the key K. And I claim that the shadows are exactly this classical information. Why is that the case? Because of this guarantee of the estimator. The guarantee says that for every K, this estimate is close, which means that shadows are actually capturing enough information to estimate all of these overlaps, like all exponentially many overlaps, with good certainty.
So this is epsilon can be 1 over polygon.
It's small constant, so think of it as 0.1.
But you wanted better than 0.1.
Good. So yes, we will amplify. That is it. Yes.
But this would be a classical.
Yes. Yeah, this is standard amplification tricks.
So sorry, 5K here, I guess I can just think of it as like you have a Turing machine that given K outputs some like quantum states. So K is that
Quantum
Oh, you mean, this psi K was the,
or the 5K here, like the qual.
this one? This is the
I see.
circuit that outputs.
Yeah.
It should have been, sorry, I used phi on the next slide. It should have been psi K.
Gotcha.
So this should have been psi K right here. And I'm saying that you give the estimator the shadows and any set of exponentially many states, it'll give you the right overlap for all of them simultaneously.
It is like a right intuition here to think of this Y like kind of like a classical sketch.
It is, exactly. Yes, it is like a classical sketch of the state. Yes.
Sorry, so
Yes.
can I, like, I'm not sure if something too sophisticated is going, like, is this just you're randomly projecting a vector to like low-dimensional space? And now you're just saying that like distances or angles or inner products are just maintained in this like...
Oh, no, the inner products are not maintained. You've randomly projected, and then there is some inefficient process. It's not as simple as just computing inner products. But there is some inefficient process that, given these projections, is able to estimate the overlap between the target state, whose projections you just computed, and an exponential set of possible states corresponding to exponentially many possible keys. And it will give you all of these overlaps approximately correctly, up to like 0.1 error, let's say, in the approximation. So what this will say is, if there is some key for which this is the right state, the estimator will say 0.9 at least overlap corresponding to that key K.
What is the role of Y?
And for all the other keys, it's going to say something like 0.1. Sorry.
EYK, what is Y?
Why is this? The input to the estimator is the shadows you collected?
It's the shadow.
Yes, the same Y. Yes. Sorry, you had it. Okay. Any other questions?
So you demand that all the cycles are orthogonal to each other, right?
I don't know.
You don't demand?
No requirement of orthogonality. Yes. Yeah.
Okay, but
This
if they
is
are close,
fairly
you may
normal.
get the same Y for.
Sorry.
If they are close.
Exactly,
you
you
may
get the
get
same Y. That's okay. But then you can also guess the same key and Yes.
The inefficient estimator is inefficient, but still If the epsilon gets smaller, does it get more inefficient? Or does it get more complicated?
I don't know, honestly. I don't think you can drive this down to below like constants.
Okay.
And I think it's only going to be a constant factor blow up. So I haven't thought about it.
Okay.
Yes. Like there is, yeah. So yes.
Is the role of this, so for every, you simultaneously need to be correlated to all E of K.
Correct.
Okay. So what is the role of that? Are you using the fact that E is polynomial-time quantum circuit? Or-
Oh, E is not. E is inefficient. E is
Is that, I meant
Yes.
the transformation from K to phi of K.
Ah,
You're
good.
using the fact that that's polynomial time?
Yes,
or-
I'm going to use that. Yes. You'll see where I use it, but it's going to come in for security. So let me just, repeat again what we just did. We took a key K, we ran the state gen on it, we got the output state, we computed its shadows and got the string Y. My claim is that if you just pair up K and Y, then first of all, these are easy to sample, right? You can easily sample K, run state. This is all efficient so far, and find Y. So you have an efficiently sampleable distribution over K and Y pairs. My claim is that given Y, it's going to be hard to find K. Now, why is that the case? Suppose finding K, given psi K tensor and like many copies of the psi K was hard, then the claim is that it should also be hard given Y. Why not? Suppose it was easy given Y, then I would just compute Y on my own. This is an efficient process. And now run the inverter that exists somehow that finds K given Y. And I'd invert psi K and find K. So really, if going back from psi K to K is hard, then going back from Y to K must also be hard. And there we use the efficiency of the shadow generation process. And now where did I use the fact that there is this estimator that estimates all the overlaps? That is in arguing that these Ys are sort of like unique. It's not like all the keys are going to be mapped to the same set of Ys. So the Ys are going to be mostly disjoint for keys that lead to disjoint or like orthogonal psi keys. Does that make sense?
So here you are like your relation is just whatever you get out of this when you input.
Yes,
K.
correct.
So a priori you expect that every K will only have like one Y. There is no. I mean, I don't
Not
know.
necessarily. No, they could overlap, but they will only have high overlaps if the psi Ks already had high overlaps. So if you had K1 and K2 such that psi K1 and psi K2, and even their n copies were pretty close, then the Ys will be pretty close. That's what the inefficient estimator guarantee says.
That's like what the word hard here is unfashionable. Yeah.
Yes. The hard is saying, if psi K1 and psi K2 are close, then finding either K1 or K2 is fine. Like if I give you psi K1, you can give me K2. This is also a good answer. Like you've won the game, you've inverted psi K1 by giving me K2 because they were close anyway.
But it's least convenient to think of them as orthogonal, in which case it's obvious from the property
Yes.
that the Y are unique, they're uniquely defined.
Yes, that's true. It is convenient to think of them as orthogonal, in which case Ys are more or less unique. You still have errors because of the way the process runs, but yes.
So your next question, this would be true for any exponential number of vectors,
Yes.
not necessarily for efficiently generated. It's probably the
Yes.
union bound. They prove that you get epsilon approximation of the inner product with exponentially small probability.
Yes, exactly.
Unless you take the unit bound.
Oh, maybe then I misunderstood your
Yes.
question. Yeah. This here we don't need the psi Ks to be efficiently generated. Okay, if that was
Collection of the.
any collection of exponentially many observables, like in fact, you don't even need to be computing overlaps with states. You define a set of observables, and these should be, you need them to be rank 1 observables, and yeah, I'm trying not to put quantum mumbo jumbo here, but yeah, you give me any collection of exponentially many quantum states, and this guarantee still holds.
Is there any hope for the estimator to be efficient or?
No, it should. If it were efficient, then well, actually nothing major would break here. But I think there are like Sharpie lower bound reasons. I can explain.
Okay,
later.
yeah, sure.
Yeah, I don't think
Isn't this sort of some like quantum version of learning? Like,
Yeah, like there's learning
you
hardness.
also don't expect the classical problem to be. I guess here you have a quantum machine, so maybe it's not such an analog.
Yeah, but we don't expect it to be efficient. Is the short answer, and I can say more.
Yeah.
Okay. All right. Okay, so let's move on.
Sorry,
Okay, so
I
this
have
is exactly how you get the
one
puzzle.
more,
Yes, please.
minor question. What is violated if everything goes to the same Y? What formal?
Good. This one.
Despite the
This
fact that they are
estimator,
orthogonal,
Yeah, everyone goes.
it cannot be.
No, I understand, but like, why do you need this?
This will fail. Oh, why do I need the
Yeah.
Y to be far away?
Yeah,
I don't need it formally. Like, formally, I'm not assuming anything except the existence of this estimator, which is guaranteed by the. Well, I'm not even assuming it. This is true. But okay, just as a thought experiment, what if we took many states and they all went to the same Y?
Yeah.
Then Y is not useful information,
right.
and I want to actually use it to measure the overlap with like a set of exponentially many states. And these are all, these should be fairly different from each other. They should be at least somewhat orthogonal, if not fully orthogonal. Like they should not be the same state. Not all of them should be the same state. And now I need my estimator to say different things for different Ks here, because these are different states. Does that make sense?
Yeah, I need to think about it more, like something is bugging me, but I'm not sure what it is.
Okay.
It's very convenient to think about the size of the orthogonal. This will help.
That, I understand that makes the task harder, and that's what, but what if they were all the same?
Yeah, then you wouldn't matter. Any K would do.
And then there's no hardness in
Yeah, then
that.
no, it's fine, the definition will.
The reduction would be fine, you
Yeah.
won't have hardness to begin with.
Yeah.
Yeah, exactly.
Okay.
Okay, so let's move on. Okay, so just to summarize, well, not summarize yet, I'm sorry. I got confused. Yes. So one last thing. So towards lower bound. So what we did so far was we looked at these examples of encryption and so on, and we extracted out the one-way hardness in these primitives. And we said, okay, one-way puzzles seem necessary if any of these things, one-way states, public key encryption, and so on, should exist. Then one-way puzzles definitely should exist. And it turns out that you could use Sharpie oracles to invert one-way puzzles. And so they exist only if P with oracle access to Sharpie is not equal to BQP. This is not too hard to see, but I was not planning to show this here, but I'm happy to talk about it afterwards if anyone is interested. But yeah, here you use the fact that there is an efficient quantum sampler that's outputting these pairs of signs. So you use the efficiency of that sampler to actually break one-way puzzles with Sharpie machines. More generally, if you have any efficient quantum process that's giving you these problems and solutions, you can use Sharpie oracles to sort of find those solutions. Okay. And you can use this to show that many natural crypto primitives like encryption, signatures, quantum money, etc., cannot exist if P to the Sharpie and BQP are the same. Okay. So this is a reasonable lower bound we have. And just to summarize, a lot of quantum crypto requires that P with oracle access to Sharpie is not equal to BQP. One exception is commitments and secure computation, and I believe this is a really, really interesting question. Like, is there any classical complexity lower bound? Any classical complexity separation that is necessary in order for quantum commitments and secure computation protocols to exist. If you haven't heard these words before, don't worry, I'll tell you what they are in just 2 minutes. Okay, going back to the second part of the talk, I want to tell you a little bit now about how to use different assumptions to build various quantum cryptographic primitives. And why am I even hopeful that this can be done? Why do I even think that there are some nice assumptions here that can be used? The first reason is this beautiful result of William Kretschmer back in 2021, who showed that there is a quantum oracle relative to which quantum primitive called a pseudo-random state can exist even if the complexity classes BQP and QMA are the same. Now, if you haven't heard of pseudo-random states, don't worry. If you've heard of pseudo-random generators, this is like a state generalization of that. Let me show you what it is. So this is just an algorithm, an efficient quantum algorithm that takes a classical string S and outputs a quantum state ket psi S. And the requirement is that the state should be computationally indistinguishable from a random state. If you know what hard randomness is, that is the requirement here. If you don't worry about it. What this says is it is a pair of distributions that are statistically far but computationally indistinguishable. So why is that? That's because the size of input to this generator is smaller than the size of its output. So you have a quantum state on a larger space of qubits, on n qubits, where the input is only, let's say, n by 2 bits long. And so the two distributions, one that you get from running the generator and outputting the resulting state, and the other distribution that you get by just output, a random string on n bits. These two distributions are statistically far, but they are computationally indistinguishable, and that's because of the guarantee that the output of this looks random. And once you have this pair of distributions that are statistically far, that means if you had all the time in the world, unbounded resources, then you could tell them apart, but with polynomial time computational resources, you cannot. Then you have a pair of distributions that is basically a cryptographic commitment scheme. This is basically equivalent. It's all you need to build a commitment. I'm going to tell, yes.
So computational indistinguishable here, do you
Yes.
get like multiple copies of psi instead of S? Or
No, just one copy.
Just one copy.
In this
Okay.
definition, you can also do the multi-copy thing. I'm
But
just
this
not-
captures
yeah.
commitments, I guess.
Yes, exactly. Okay, now if you haven't heard commitments before, don't worry about the last line again. All we care about is getting to this pair of distributions that are A, computationally hard to distinguish, but B, statistically distinguishable. They really are different distributions.
So the result in the previous slide of Kurtzman says that such a generator
Can exist even if,
really can exist.
right, relative to an oracle.
Relative to a quantum
Exactly.
oracle, right.
Relative to not even a random oracle.
Quantum.
It is a quantum unitary structured oracle. But relative to that oracle, there is an oracle relative to which pseudo-random states exist, but BQP equals QN. So we don't know how to build these. This is still open, like build this from any interesting assumption that is not just one-way functions. We don't know how to do that. Okay. There was some other follow-up works that had other oracle feasibilities of quantum cryptography, even when, let's say, P equals NP, or there was a paper of Lombardi, Ma, and John Wright that said that relative to a classical oracle, it is possible. Let me explain what I mean by it is possible. It's possible that commitments and pseudo-random states can exist, even if all problems that can be classically described can be easily solved. So basically, they consider the all oracle. You give it any classical problem, it solves it for you. And they show that one single query to this oracle cannot break quantum commitment. 2 queries or more, they conjecture that even with 2 or more queries, we cannot break quantum commitment, but we don't know how to prove this. So this is where the oracle separation results are. But overall, that means there's a strong possibility that quantum commitments can be based on assumptions that are at least mathematically weaker, or maybe even true, even if P and NP are equal. Okay? And so that's going to be the goal or the focus of the rest of the talk, is to just find these assumptions and build quantum cryptography from them. Okay. And not just commitments, may be possible for signatures, encryption, and so on. And so before we go there, just to give you a recap of the landscape of various complexity classes, this is P, which is the class of all efficient computations, and BQP, the class of all efficient quantum computations. And then we have NP, which is the class of all languages that can be efficiently verified given a certificate whose solutions can be efficiently verified given a certificate. And then beyond that is the polynomial hierarchy, and beyond that even is sharp P, or here I write it as P with oracle access to sharp P to make it a decision class. But this is roughly what we believe, like this is what we believe these containments of these classes look like, and this is an increasing order of hardness as we go up. So the hardest problems lie somewhere here, and the easiest ones lie here. And we want to pick the hardest ones.
The sharp P can simulate quantum.
Yes, so BQP lies in P to the sharp P, but is believed to be outside of, not contained in PH. But yes, P to the sharp P can simulate quantum computations, which is why BQP is inside this big circle up here. Indeed. And so for classical cryptography, we can only pick problems from this green circle, because again, we need NP to be hard. So, we can only pick problems that are in NP. For quantum cryptography, and in particular, if you want to build one-way puzzles, which is what I was showing you, before, then it's possible that you can pick problems out here in this big blue circle out here. And that's exactly what we're going to try to do. We want to build this primitive called a one-way puzzle. We call it sampling pairs of classical strings X and Y that satisfy some relation. I don't care if it's efficiently checkable or not. The only guarantee I want is given Y, it should be hard to find any X that satisfies the relation. Why do we want to build one-way puzzles? Well, we were using them as a lower bound last time, but it turns out that they can yield commitments. So in this paper with Kabir from 2024, we showed that one-way puzzles give you commitments. And we use this, basically we used one-way puzzles as a bridge. We use them as a bridge to show that public key encryption and signatures and one-way state generators, all of the stuff I showed you in the first part of the talk, all of that implies the existence of cryptographic commitments. And commitments imply secure computation. This we showed in some older works a few years ago. So I just want to, these two words may be new for some people, both commitments and secure computation. So before I move on, I want to explain what these are. Any questions so far? Okay, yes.
And I guess you think that commitments might be easier to construct than one-way puzzles? Is that what you're saying from that?
Yes, maybe easier, but the route we will take is we will build one-way puzzles. Okay, so what is a commitment? A commitment is like the digital analog of a locked box. It allows you to take your message, put it inside this box, send it across to the receiver. Receiver cannot open the box because it's locked. The message remains hidden from them. Later on, the committer can send a key to open the box, and the receiver can open and read the message end. And the guarantee is that because this box was sent in advance, in this later stage, what is inside the box is fixed to M and cannot be changed to anything except M. Now, we don't really want to be sending boxes to each other, which is why we do cryptography. And so commitment is really a digital analog of this process. The committer and receiver interact, they commit. The committer commits by exchanging messages with the receiver. And at the end of this message exchange, they have a transcript. At this point, the committer is committed to a message. This message remains hidden from the receiver, but the receiver also knows that later on, the committer cannot change their mind about what they committed to. So later on, the committer sends a decommitment. Think of it as the randomness that they use to generate these messages to the committer. And given this randomness, the receiver can indeed check that the committer committed to M. The guarantees that you have here, just too far back, but the guarantees that you have here are hiding and binding. So at the end of the commit stage, the message remains hidden from the receiver. In the decommit stage, the committer cannot open to anything except the intended message. Now, why do we care about building it? First of all, this is really useful in many places, but to convince you, let me give you an even more exciting application. So it turns out that if you have commitments, then you can build this really beautiful central primitive in cryptography called secure computation. What is secure computation? It allows two parties that have their own private information to collaborate and compute a joint function on this private information while keeping their information hidden from each other. And more generally, it's not just two parties. You can think about many parties that have their own private data. They can collaboratively train models, compute on this data without ever sharing anything with each other beyond the intended output of the computation. So this is really beautiful, really central and useful primitive in cryptography. And it turns out that once you have quantum commitments, using more quantum information trickery, you can build secure computation. So this is really only possible if you use quantum info. Classically, this is impossible. In fact, like there are separations. You cannot build secure computation from commitments, but quantumly you can. And so that's why we're targeting building these primitives. And now the goal is, can you do secure computation without assuming one-way functions even from just Sharp-P hardness? And hopefully have convinced you through these implications that it would suffice to prove that if P to the sharp P, P with Oracle access to sharp P, and BQP are separate, then one-way puzzles exist. Because I already showed you if one-way puzzles exist, then commitments exist, and if commitments exist, then secure computation exists. Although I didn't show you how. Yeah.
So in quantum commitments, are you committing a classical string or a state?
Yes, to a classical string.
I see. So only the protocol itself is
Quantum, yes. The protocol is using quantum information, but you're committing to a classical string. Exactly. Just like in the diagram, you were locking a classical message in a box. Yeah, that's all classical. It's only the communication and the resources used by the participants will need to have some quantum components. Okay. All right. So any questions so far? All right, Sharp-P is a counting complexity class. And for example, it captures the complexity of answering how many satisfying assignments does a given Boolean formula have. There's also this beautiful Sharp-P complete problem, which is the problem of computing the matrix, the permanent of a matrix. So this is just like the determinant, which I hope everyone is familiar with, except there's no minus signs there. It's all, you're just adding up all the terms. So this is the problem of computing the permanent of a matrix. This is known to be Sharp-P complete in the worst case. It's actually also known to be Sharp-P hard in the average case for many natural distributions over these matrices. And this is great for crypto. Cryptographers are always looking for average case hard problems. This is a beautiful problem that already has average case hardness. So when Kabir and I started out, we were like trying to understand this problem and trying to see if we could just build quantum cryptography from the hardness of computing these permanents for these natural nice distributions over matrices, where we know it's already average case hard. So the main issue that we encountered was the following. Recall that the puzzle sampler needs to be an efficient quantum machine. We need an efficient quantum machine that samples these X and Y pairs, but given Y, it's hard to find X. So we could try to set X to be the hard part, which is computing, which is the permanent, and Y to be the easy, with the public part, which is the matrix A. So set X to be the permanent of the matrix and Y to be the matrix itself, and say, okay, maybe this is a reasonable way to build a one-way puzzle. And of course, the difficulty is that we would need to quantumly efficiently sample these pairs of matrix and permanent together. And this turned out to be hard. We tried and we kept failing. So this fairly convinced that there are not natural distributions over matrices for which it is easy to efficiently sample both the matrix and its permanent. And we need this efficient sampleability in order to build efficient cryptography. And this is where this, let me give you, this is a quick detour into this beautiful literature. Yes.
If you go back to the previous slide and you asked, suppose you didn't put quantum there, so you efficiently sampled. Do we know that's impossible? Like P to the sharp P is not equal to NP or something like that? Like, does the question make sense? Like, if you tried to have this sampling procedure that hits this average case sharp P hard task,
yeah, I think it would.
Okay.
Would be my guess. I will think more after the.
Okay.
Yeah. Good question. Sorry, it's not. Okay, but right. Our goal is to now somehow have some efficient process here that's giving us hard problems. And it doesn't seem like with this permanent problem, we can get this efficient process easily. So we'll take a more convoluted route to getting it. And our route involves looking at these quantum advantage experiments that are called boson sampling, random circuit sampling, IQP sampling, so on in the literature. These have gained a lot of press coverage recently, so maybe you've heard the word random circuit sampling, but don't worry if not. What the goal of all of these experiments is to demonstrate that there are certain tasks that quantum computers can do that classical computers cannot. And in particular, they look at sampling tasks. So they set up the quantum computer to be some random quantum circuit. They run this circuit, take the state output by the circuit, and measure it. And this generates a distribution. And the goal is to say that this distribution cannot be classically simulated. And okay, let's forgetting for a second about what they're trying to do there. The main takeaway from that setup is the following. Quantum circuits can efficiently sample from some distribution such that the probabilities of outputs of these quantum circuits encode the permanence of certain unitary matrices. So what this entire literature is telling us, or the one takeaway from there, is that if permanence of matrices are hard to compute, then there are efficient quantum processes such that the probabilities of outcomes of these quantum processes are actually hard to compute. And this so far is just true. Now, so that means instead of using permanence, we could try to use this hardness of computing probabilities to build puzzles. That will make it a little easier to think about things. So what those experiments, again, are telling us that there are efficient quantumly samplable distributions such that for a random output of this distribution, it is hard to compute the probability assigned by the distribution to this output A. So let's try what we were doing before again. Let's try to set X to be, the key of the puzzle, the hard part, to be this probability value, and Y to be the output A. Does anyone see any issues with this?
Can't we just sample and check this?
Oh, A is given to you. You want an outcome with A in it. That's it.
So it's how do you efficiently sample X and Y again, right? The goal is to efficiently sample X and Y pairs. Here now you want to sample. What this is saying is there is a distribution that samples strings A. So it's sampling A, but how do you get the probability of A along? This is hard. So it's the same problem as before, which is this joint distribution of X and Y, which is A along with its probability, is hard to sample. What is easy to sample is just A by itself. So does that make sense? All right, so then all that is easy to sample is just the A. So it turns out that we'll take a detour again, small detour, but we'll define this distributional variant of a one-way puzzle, which may be actually in retrospect the right way to look at it all along, which is there is an efficient quantum sampler. Again, it outputs X and Y pairs. But now instead of saying that given Y, you can't find any X that satisfies the relation, I will just say given Y, you cannot reverse sample X from the right distribution. In other words, any adversary that's given Y that is reverse sampling X should be at least inverse polynomially far from the right distribution of reverse sampled X.
Statistically or computationally?
Statistically.
Yeah, statistically inverse polynomially far, but the adversary is a computational machine. Yes. So, and turns out that distributional one-way puzzles and one-way puzzles are equivalent. Okay. So now, given this reverse sampling way of looking at things, let's just go back here. What we had is there is an efficiently samplable distribution over A's, and all we know about hardness is that the probabilities of these A's are hard to compute. So let's use some indirection, and my claim is the following is a distributional one-way puzzle. You sample a string, say that the string is n bits long. You sample I, which is in 0 through n minus 1. It's going to tell you where to truncate your string. and you simply truncate your string. Oh, this should have been I here. I'm sorry. So this should have been just, you truncate your string to a random point. That's going to be the Y. And X, which is the hard to find part, is just going to be the next bit. So my claim again is that if I were to sample an A from this distribution, randomly truncate it to the first I bits and output them, and ask the adversary to sample the next bit, then this is going to be hard. And here's an oversimplified proof about why this next bit sampling task is hard. Suppose you have an adversary that, given any prefix, samples the next bit perfectly for all prefixes. This is not going to be the case. We'll have to deal with errors. But suppose the adversary worked perfectly. Then we can approximate these probabilities of different strings A in the following really simple way. We start running the adversary on bot to approximate the probability that they output, the probability of outputting is 0, which is the next bit. And recall that the goal is to approximate the probability of this particular string, 0, 1, 0, 0. So now we've approximated the probability of 0. Next, we will approximate the probability of 0, 1. How? We run the adversary on 0 many times to approximate the probability that the next bit is a 1. This gives us an approximation for the probability of 0, 1. And if you have multiplicative errors here, they combine nicely, this still works. Then you run them on 0, 1 many times to approximate the probability of 0, 1, 0, and keep going on, and you can use this to approximate the probability of any string. So this is so what this is saying is that given an adversary that samples the next bit perfectly on all prefixes, there is a machine that approximates the probabilities for all strings A up to some inverse polynomial relative errors. And note that even approximating here is incurring errors. That's because we cannot run the adversary forever. We're running it only polynomially many times. And so, even if we had a perfect sampler, our approximator has some errors. But this approximation task is sharply hard in the worst case. So if we had a perfect adversary, then we would be contradicting worst case sharply hardness. Does that make sense? Now, the problem is we don't have a perfect adversary. For cryptography, we always have to allow the adversary some inverse polynomial errors. And when we allow those errors, then the adversary can pick some strings A and just be completely wrong on them. And so now our approximation is also just going to be completely falling apart on some fraction of the strings A, but it will be good on the remaining strings. And so what we need to assume to build one-way puzzles is that there is a quantumly efficiently samplable distribution such that quantum polynomial time machines cannot approximate the probabilities of outcomes up to inverse polynomial times 2 to the n additive error for all the instances. So this is the formal statement. You can think of this as basically the adversary should not be right everywhere. Like they should be wrong on at least inverse polynomially many of the A's. And it turns out that the literature in sampling-based quantum advantage, boson sampling, random circuit sampling that I was telling you about, that conjectures that this particular assumption or that this particular problem of approximating these probabilities is sharply hard. Or this average case problem is sharply hard. In particular, these quantum efficiently samplable distributions, they correspond to different types of quantum circuit distributions. So with boson sampling, this problem is about the permanence of random matrices that have n01 Gaussian entries. And then they show how to embed this into a boson sampling distribution. Similarly, with random circuit sampling, this talks about taking a random quantum circuit, and they show that they conjecture that, again, the probabilities of outcomes of these circuits are sharply hard to approximate on average. And really, all of this literature needs these problems to be much harder than NP, because all of their proofs rely on techniques that use NP oracles and so on. So they really need that these problems are at least beyond some levels of the polynomial hierarchy, if you're familiar. But really, yeah, so these really are conjectured to lie outside of NP. And if they were to be in the class NP, then all of this literature, the foundations of this literature would collapse. Okay, so just to summarize, the main theorem is that assume any of the conjectures that I showed you, on the previous slide, right? Assume any of these specific conjectures from the quantum advantage literature. Then one-way puzzles exist if and only if P with oracle access to sharp P is not equal to BQP. And I want to conclude by just saying a little bit about the assumption. The hard problem that we're assuming here is that there is a quantumly efficiently samplable distribution such that approximating the output probabilities is hard on average up to like a certain additive error. How hard is this problem? Like, is this harder than the problems that we use to build classical cryptography? And I was just arguing that quantum advantage literature conjectures that this is sharply hard, so much harder. In fact, they rely on this problem lying outside BPP with oracle access to NP. And so if you could use this same problem to build classical cryptography via BPP or polynomial time reductions, then BPP with oracle access to NP would solve this problem. This would contradict the quantum advantage conjectures. So all I'm saying here is that if you could use this to build one-way functions, then you'd be doing something very interesting and contradicting all the quantum advantage conjectures. So we don't expect you to be able to use this.
Say again, if you could.
You said something the opposite of what you said before.
Oh, did I say that? Okay.
Yeah, you want this to be hard. So
we want this to be hard.
So you want to use this for quantum crypto.
Yes, here I'm saying if you can use this to do classical crypto, like one-way functions. If you can use this problem to build one-way functions, then this would be super surprising. Then this would contradict all the quantum advantage conjectures. Why? If you use the BPP reduction in particular to build one-way functions from this problem, then BPP with oracle access to NP will solve this problem. Why? Because NP oracles can break one-way functions.
Oh, I see.
Does that-
There was a reduction from this.
To one-way
To
functions.
one-way function.
Exactly.
Then BPP to the NP would break the one-way function, therefore breaking, well, a certain
NP would break the one-way function.
sub-instance of this maybe, or who knows.
Right, okay. In general, yes, certain sub-instance of this, and that sub-instance would contradict, would not correspond to a quantum advantage circuit. So here you really should be using the same circuits for which you believe that quantum advantage holds.
Okay.
So if you take this assumption, you remove the quantum from it, right?
Good, I'm getting to that. This was getting to that. So we don't expect even BQP or PH. So this is not even just BPP reductions, we don't even expect other strong reductions here. So in summary, we don't expect this problem to give us one-way functions for circuits where this really is a quantum circuit, for which we believe there is no classical circuit that samples from the same distribution. In fact, if there was a classically efficiently samplable distribution with the same hardness properties, then what does this say? Turns out that this is actually equivalent to the existence of one-way functions. So if I replace the word quantum sampler with classical sampler here, then this is precisely another way to define a one-way function.
And this hard problem isn't Holloway hierarchy.
Yes, this is an NP.
Although the 2 to the n is not there.
Sorry?
I don't think that 2 to the n.
Additive error. So because the probabilities are 1 by 2 to the n-ish. So if you think about relative error, then this is 1 by pn.
Yeah.
Yes. So if you want to think about relative error, this can just be 1 over poly, but I'm talking about additive error, so adding the 2 to the n. Okay. So just go, yes.
Do you think that should make us more suspicious about the assumption, that it lies in NP when you look at the classical thing? What do you think?
No, I think there's no reason for the quantum version. In fact, the classical version lies in NP, and the quantum version really should not lie in NP, because if well, if you believe all of these quantum sampling experiments or that a random quantum circuit can sample from these distributions that classical circuits cannot. If you believe that, then I would say that you should believe that this should lie well outside of NP.
Okay, yeah, I agree. Problem should be a hard problem, but like maybe it makes me suspicious that it's sharply hard.
Okay, that I'm not, okay. Perhaps the gap between this problem and worst case Sharpe hardness is similar to the gap between one-way functions and worst case NP hardness. Maybe this is a hard gap to overcome, I don't know. Or maybe it's easy, I don't know. But this is like an average case approximation problem, like approximating probabilities problem. And yeah, it's.
I see. I guess in the classical case, it's exactly the difference between one-way functions and worst case NP hardness.
Correct. Yes. In the classical, yes, exactly. So in the classical case, this is precisely a one-way function. So we don't, well, it's probably hard to prove that this is worst case NP hard because this is a one-way function here. The quantum case, I don't know. Maybe this is saying that this is also going to be hard to prove that it's Sharpe hard worst case. But it should still be pretty much harder than NP, I would argue. Okay, so let's yeah, so the quantum version of this problem is equivalent to one-way puzzles. You can think of this as like some type of average case Sharpe approximation hardness. And the two works of Cavalier, Golden, Gray, Hall, and Hiroka Moremai looked at a very similar problem, and they proved a similar equivalence between one-way puzzles and this type of probability approximation. But they were trying to connect Kolmogorov complexity of strings sampled by quantum distributions with the existence of commitments. Also, the errors there are different for our case because we want to use these quantum advantage conjectures and so on. We really care about inverse polynomial errors. They have constant errors. But yeah, I just want to mention that there are related works on Kolmogorov complexity. Okay, so just to summarize, what we showed is that probability approximation hardness gives us one-way puzzles, which gives commitments in secure computation. I'm out of time, so I'm going to skip this part completely. Just summarize, maybe we can go for commitments and for puzzles, we cannot.
You can do your summary, it would not be a bad idea, as the previous slide has.
Okay.
Yeah.
Here?
Yeah.
Okay. So, so in summary, in summary, classical cryptography picks problems from the green circle. Here we've picked problems from the blue circle, which are hopefully much harder problems right here, and use them to build quantum commitments and secure computation. It would be even nicer if we could pick even harder problems, maybe problems in P space, maybe beyond, and build quantum commitments and secure computation from them. We don't know if this is a hard bound. That I think is a really interesting problem. So we know that this is a hard bound for one-way puzzles, but we only have very few interesting ways to build quantum commitments right now, and one of them is via one-way puzzles. So this is a bound on this particular approach, but maybe there's other interesting ways to do this from problems outside this, or maybe there's a lower bound there. I don't know. Maybe this is the best we can do. We really don't know. Also, I focused on commitments and secure computation for these constructions. But what about quantum encryption, signatures? There's this thing called quantum money, which is really interesting and cool. We don't necessarily need to restrict ourselves to classical crypto problems, like the same classical crypto assumptions, in order to build them. We could pick problems from these like quantum circles or like these harder problems and use them to build interesting quantum crypto primitives beyond commitments. That would be very nice too. And so let me just end with some open problems. The first is, can we build quantum cryptography from worst case hardness? So the goal was to just assume P with oracle access to Sharpe is not equal to BQP in the worst case and build quantum cryptography from it. We did not succeed because we had to use these extra conjectures. So can you do this from worst case Sharpe hardness or even just worst case NP hardness? So just assume NP is not equal to BQP. Worst case, I don't know. Or can we use new physical sources of hardness to build cryptography, like the hardness of decoding black hole radiations or recognizing phases of matter, etc.? Can we get stronger connections between quantum advantage and cryptography? For example, one of the things we do is we show if certain conjectures made in the quantum advantage literature are true, then quantum cryptography exists. It'd be even nicer if we could say something like, if quantum advantage exists, then quantum cryptography exists. That would be nice, but I don't know how to do it. And then lastly, and these two bullets are sort of related, what about quantum cryptography, where some agents are classical and others are quantum? And so in these cases where you insist on classical communication between them, can you use other physical resources to build cryptography in these settings? And that I want to summarize. Thank you so much.
Yeah, I guess we're a bit over time. We can take questions.